Hey, good morning, everyone. Sorry I'm a little late. I was in my office hours and I had some students in there asking for help, so lost track of time. So hope everyone had a great weekend. I had given you some problems to work on. Any questions on those problems for homework? I asked you to finish this graph and try and do these two. Figure we could go through some of this. Are you all there? Can you all hear me?
I was going to ask if we could go over the first one.
So you mean the first one, this one here?
Yes.
Or, yeah, we can go through that one. Let me draw the graph because I asked you to go ahead and finish up this graph. Let me show you what this could look like. Yours should look very similar. It should flatten out towards that magnet. The vertical asymptote should force it up like this. Then on the other side, you should be going down. You should connect here, and then you should force up. And then on the other side, you should be forcing, the function should be forced to go down, connect the dot, and then just flatten out towards that. Something like that is what you should have on that graph. Now, as far as this one is concerned, we can do this one. And I'll just run through the whole thing. I'm going to take these steps. Let me copy this whole page. Okay, so we're going to go through these 6 steps to sketch this function. So the first step is to find the X-intercepts, and to do that, we set the numerator equal to 0. So we set this equal to 0. I'm going to move through this quickly because I realize that you've already done the work for a lot of this. So if you have a question on any of these steps, please just let me know. Set the top equal to 0 and factor it. You could also use a quadratic formula, but you should get 2 answers, 5 and -1. So are there any questions on that part? The X-intercepts? Okay, the vertical asymptotes, we set the denominator to 0. I can do a GCF. I can factor out an X. That leaves me with X squared minus 9. And then we have to realize that that turns into, the X squared minus 9 turns into X plus 3 times X minus 3. And now we have 3 answers here. We get 0, -3, and 3. And now the third step is the horizontal asymptotes. And for that, we have to look at the degree of the numerator. So the numerator has a degree of 2. And the denominator has a degree of 3. So in other words, the numerator's degree is 2, and that is smaller than the excuse me, denominator's degree, which is 3. So you have to go back to your notes, and I gave you a set of cases last time right here, how to find horizontal asymptotes. You look at the degree of the top and bottom. If the degree of the numerator is smaller than the denominator, then y equals 0 is the horizontal asymptote. And that's the same as the x-axis. And that's the case we have here, right? 2 is smaller than 3. So we are going to use this case. This tells me that because of this, the x-axis is the horizontal asymptote. Any questions on that? All right, step 4 is to draw a graph that has basically all this information on it. So I'm going to go to a graph here. And I'm going to start with my X-intercepts at 5 and -1. So I go to -1, I go to 5. And here I'm going to put actual dots because these points live on our graph. And then I'm going to do the next thing, which is the vertical asymptotes. Those are 0, -3, and 3. Those are going to be vertical barriers, those vertical dotted lines. So at 0, 3, and -3, here's 3. -3 is over here. And then another one at 0, which is the y-axis. So it's kind of hard to draw it. So make sure you see that there is a barrier here. And then the last thing is we have a horizontal asymptote of the x-axis. And I said in class, be very careful with this. I do not want to draw a line all the way across the x-axis. The horizontal asymptote only tells you what's happening at the edges of the function. So I'm going to put dotted lines over here on the x-axis on the left and right edges. And those are my magnets that will pull my graph towards it at the end. Any questions? The fifth, go ahead.
I was gonna say, in the last class, I remember you had said if you made one little mistake, I'd seen where I messed up. I didn't change on the first step, the 1 and the -5. So I ended up, so I'm getting the graph that we have, but it's just flipped.
So you have -5 and +1?
Yeah, that's what I ended up doing.
Yeah.
Now I see what you're saying. One little thing from the beginning and it'll throw it all off.
Yeah, and as long as you're showing your work on the tests, if you're showing your work on your test, then I can see those mistakes, you know, and I can give you partial credit for that. Okay, now we need test points. So the test points, this is always confusing to students, how many of them you need and where they should be. So here's one way to look at it, if this makes it easier. You're always going to need one test point on each edge. Okay, so something over here, maybe -6, and something way over here, like maybe at, let's say, 10. Okay. I'm doing these, notice I'm marking them with little X's. I do not want to confuse these with X-intercepts. I do not recommend that you put dots here because that's going to confuse you, all right? So, and I'm circling them to really kind of distinguish them from everything else. These are my test points, one on each edge. And then what I do is all I'm looking at are my verticals and my X-intercepts. So I have a vertical here and an X-intercept here. So I need to figure out what's happening between here. So I need to pick something in here, like -2. Unfortunately, I need one also between this X-intercept and this vertical, and this is -1 and that's 0. So I have to pick a fraction. That's going to suck. I'm going to have to pick maybe like -1/2. And then I have this vertical and this vertical, so I need something between those two. Maybe I can pick 2. And then I have a vertical and an X-intercept, so I need something in between those two, so I'll pick 4. So in total here, I have 1, 2, 3, 4, 5, 6, right? 6 test points. And I told you, you'll always have one more than the number of X-intercepts and verticals together. So I had 2 X-intercepts and 3 verticals, that's 5. We should have 6 test points. Any questions on that? What do you do with these test points?
You plug them into the formula or the
We have to plug them into this. That's going to suck. This is tedious work right here. But remember, the only thing I care about when I do this, the only thing I care about is whether or not I get a positive or negative answer. Because we're just trying to figure out if the graph is above or below the x-axis. So let's start by plugging in, let's do -6 first. Now I'm going to do this kind of quick, okay? If I do -6 into the top, I get 36 minus 4 times -6 minus 5 all over. All right, so we take -6 and we cube it. What's -6 cubed? Is it a positive or negative? Take a negative number and raise it.
Negative.
Negative. Here, I'll do it like that. I'll back up. Let me back up and do it a little slower here. So I'm plugging -6 into everything, right? So we've got 36. And then we take a negative and negative together. That'll be plus 24, then -5. So really all that matters to me is that the top is positive. Do y'all agree? Top is a positive number. Okay, now on the bottom, I'm gonna get, when you put these together, you're gonna get a negative number on the bottom. And so you get a negative on the bottom, and a positive over a negative is negative. And what that tells me is that when I'm at -6, I have a point below the x-axis. So I'm gonna move it down like this. Okay. And I have to do that for each of the other points, which is, like I said, it's gonna suck, right? So do you want me to actually show you all that work or just tell you what happens? I mean, I would say you need a calculator here for this just to make it go quicker. All right.
I mean, if anything, you could just tell us because maybe we all pick different test points.
Yeah. So if you had picked a different test point, like let's say you'd pick -4 instead of -6, you should still get a negative answer. As long as we all pick something to the left of -3, we should all get something negative. Same thing in between here and here. No matter what point you pick, we should all get something. It'll be positive on this one. So I'm gonna put a point above. If you go to -1/2 and plug in to here, everyone should get a negative number. So I'm going to put a point up. You know what? I want these in red because these are actually points on my graph. So I have a point below, I have a point above. Here I'll have a point below. At 2, it'll be above. At 4, it'll be below. And at 10, it'll be above. So in other words, when you plug in -6, you get a negative number. When you plug in -2, you get a positive number. When you plug in -1/2, you get a negative number. When you plug in 2, you get a positive. 4 negative, 10 positive.
Excuse me. I didn't for the -2, I didn't get a negative answer. I got positive.
Okay, let's try it. So f of -2, you do -2 squared minus 4 times -2 minus 5 all over -2 cubed minus 9 times -2. Okay, -2 times -2, so -2 squared is going to be 4. Then you're going to have -4 times -2, that's +8, and then -5 over -2 cubed is -2 times -2 times -2 is -8. And then -9 times -2 is +18. So your numerator is 12 take away 5, that's positive. And then you do -8 plus 18, that's also positive. And a positive divided by positive is positive. Which is what happens at -2, you should be up here somewhere. Do you see what you did?
Yes,
Okay. So we're in agreement now?
it's fine. Yeah.
Okay, good. Okay, now I'm going to connect all these dots together and try and draw a picture. So I'm going to start with the leftmost point that I see, which is this one I highlighted in yellow. Out to the left, I have to go up towards that magnet. Flatten out towards it. To the right, as I'm drawing, I have a barrier in my way. So I have to either turn up or down. We talked about this last class. Why can I not turn up?
Because you have the barrier, the magnet barrier.
Nope, it doesn't have anything to do with this one.
Oh, I mean on the axis right there. The dotted line goes through it.
Because you are creating another X step.
Yeah, we cannot cross the x-axis here. We are not allowed to, but it's not because of this barrier. It's not because of this dotted line on the edges. It's because when we were solving for the x-intercepts, we're only supposed to have two. We're only supposed to have one at -1 and at 5. And if you draw your graph like this, you've now created another x-intercept that doesn't belong there. Okay, so that's why you cannot turn up. You have to instead turn down like this. Does that make sense, John?
Yes.
Okay.
Yeah, that's what I ended up getting. I just didn't explain the
Yeah.
proper reason why.
Okay. Yeah, I just want to make sure y'all are not, thinking about this dotted line right here, this horizontal. It does not go all the way through the middle of the function. It only goes through the edges. Because like even here, when we go to the next point, which is this point here in yellow now, when I draw this to the left, I have to go up because I can't turn down and have an x-intercept. But when I go to the right, I do want to cross through the x-axis. See that? I am going to cross through here. And if you think that this dotted line goes all the way across, you're going to be, like kind of hesitant to do this. I think you'd be hesitant. So I go up here, connect, and then to the right, I'm going to have to go down. Excuse me. What about the next point? This one's interesting. To the left, what has to happen?
It has to go up.
And to the right?
Up.
Up, right? So on both sides, it goes up. It's going to look almost like a little parabola. It's not a parabola, but it looks kind of like a parabola. I can't turn down here. I have no x-intercepts in between here. Then I go to this point. To the left, I have to go down. To the right, I connect the dot. See, I cross through the x-axis here, right? That's okay. I go up to this dot, and then I flatten out towards my magnet. These are tedious, huh? There's a lot of things you have to keep track of. A lot of little things that you can make mistakes on. So just make sure on your test that you're showing me as much of that work as you can. Like John said earlier, like if you put -5 and +1 here, your graph's going to be all wrong, but I'm not going to say then that you get no points. I'm just going to make sure that what you have based on your mistake is correct. Okay, any questions on this?
No, but do we have time to go over the other one?
We can make time.
Thank you.
Yeah. I have no problem doing this one. As you might imagine, on your next test, I can really only give you like one of these to do, right? You're gonna have other stuff on the test. These problems take a while, so I can't give you like 10 of them, right? I can only give you like 1 or maybe 2 of them. So that means your next test is not going to be a lot of problems. It's going to be just a few problems. And so if you get one of them wrong, it could have a huge impact on your grade. That's just the nature of the next test. It's just not a long test. It's not long in terms of the number of problems. Okay, so let's run through the steps. First step, I'm going to find the x-intercepts. And for that, I set the top to 0. I move the 8 over. I divide by 5. Now we are going to need to graph this. So it might be worth making this a decimal. -1 point, what is it?
6.
6, okay. All right, so I have 1 x-intercept, that's good. All right, second step, find my vertical asymptotes, if I have any. For that, I set the denominator equal to 0. I pull a GCF out, they both have an X. And I set both of these equal to 0. I get one answer is 0. The other one is -5. Move the 5 to the other side. Third step, horizontal asymptote. And this is the same as the previous problem. The degree of the numerator is 1. The degree of the denominator is 2. And when we compare those, the numerator's degree is smaller than the denominators, which means the x-axis is our horizontal asymptote. The fourth step is to draw my picture. If I'm going too fast, let me know. -1.6. I have an x-intercept. At 0, -5, I have vertical asymptotes. And then I have a horizontal asymptote of the x-axis. So I draw out like the same thing we did on the last one. I'm gonna need 4 test points. 1 on each edge. I'll do -6. Over here, I can do anything. I don't know. How about 2? Then I need 1 in between here and here. How about -3? And then 1 in here. I think -1 is a good one there. And I have to plug those in. So let me do those test points plugged in. Let me do it up here. If I plug in -6, I get 5 times -6 plus 8. And then -6 squared plus 5 times -6. The top is negative because I get -30 plus 8. And the bottom is also negative because I'm going to, no, sorry, the bottom is positive. It's 36. Take away 30. So that's positive. So a negative over a positive is negative. And that means when I go to -6, I have a dot that's below the x-axis. Are we good? That makes sense, everyone?
Yes.
The next 3 are going to be, it's just going to keep switching. It's going to be positive here, then negative, then positive. Now, look, be careful. On a test, you need to check each one. It switches back and forth here. And the reason I know that is because I understand rational functions in a different way. So I know that's what's going to happen. But it doesn't always have to happen. Because students will always ask me, can I just find the first one and then just make all the other ones switch? Right? That'd be nice if that's what happened all the time, but it doesn't. So you have to check each one. And now we draw a picture. So out the left, I go up towards the magnet. To the right, I drop down. On the inside, I go up on the left here, connect the dots, goes down. And then this last one, I go up here as I go to the left, and then I flatten out as I go to the right. All right, so we've gone through the homework problems now. I hope that that was helpful. I will give you a review for the next test. Let's see, when is our next test? I think we're still a little ways off on our next test. Let me check. Is that right? Have we had? Oh no, October 28th. There we go. So we still have, oh, that's next week already? Wow, okay. So next Thursday, we'll have our 3rd exam. So I'll give you a review by this Thursday. Okay, this week I'll give you a review for you to prepare for the test. Okay, I'd like to talk about today's stuff. And we're going to briefly continue with rational functions. And then after we do that, we're going to move on to the next type of function, right? We're almost done with functions. We have 2 more to talk about. So I thought what would be good is to actually talk about a real world problem. So I don't know if you have ever heard of this, but these things called zebra mussels, they're a mussel, okay? I don't know if you know what a mussel is, but it's a living creature, right? Has a hard shell on the outside. The mussel lives inside the shell. These things have been infesting some of our lakes in Texas, and they're very, very difficult to control. And they're not good. They cause all sorts of issues with the water quality, and they're not native to the lakes. They've been brought in from the outside, and now that they're in the lakes, they're just really, really difficult to control. And there's a lot of repercussions if we don't try and somehow mitigate the problem, right? So this is just an article about the mussels and what kind of harm they cause, and you can see how they're like all over this right here. There's a lot of lakes. People use the water from the lakes to irrigate, and you know, farmers that live around the lakes, they use that water for their farms. And these mussels get into the pipes, and they get into the motors, and they clog everything up. And it's just on top of the ecological problems they cause, there's other issues, right? So I'm not here to talk about what to do about this, and honestly, it's not something I think about every day, but it's a problem, right? So you can try and clean it up. You can try and clean the lakes, all right? But the problem is it gets, the more you clean, the more expensive it gets. So I want you to consider the following function, all right? I'm going to show you a graph of a function here. Let me zoom in on this. Well, let me zoom out first. Does everyone agree that that kind of looks like a rational function, right? It kind of has those properties that we've been talking about. Vertical, it looks like it has a vertical asymptote. Looks like it has a horizontal asymptote. Looks like it has an X-intercept, right? Well, this function I have written here on the left side is actually the function f of x equals 10x over 100 minus x. Now, what does this have to do with zebra mussels, right? Well, this function represents the cost in millions of dollars to clean X% of a lake. All right. So what in the world does this mean? It means if you tell me you want to go clean this lake, and you tell me what percentage of the lake you want to clean these mussels out of, X will represent that percentage, okay? The output of this function will tell you how many millions of dollars it's going to cost you to do that, all right? So if I want to clean 0% of the lake, then it shouldn't cost me any money, right? 0% should be free, right? I'm not going to clean the mussels, we're just going to let them be. That should be free. Make sense? And can you see on this graph that if you plug in 0, right? So 0%, the X coordinate is the percent you want cleaned. The Y coordinate is the cost in millions of dollars. So 0%, no problem, it's going to be free. But what happens is we try and clean more? Like what if we try and clean 1% or 2% or 3%? Let's make this go to like close to 1 here. So look at that. If we try and clean 10% of the lake, it's going to cost us $1.1 million. It's going to be very expensive. Make sense? But because it's so difficult, because you have to, yes, you could go to like maybe go to the shoreline and clean it. That'd be easy. You get a bulldozer and you scrape up the shoreline, but you still have to get all the mussels that are in the lake, right? And that gets more and more expensive to get the ones that are below water, right? Living on rocks underneath the, underneath the surface of the water. So what we should expect is that the higher the percentage, right, the more expensive it gets, right? We try and do 20%, 28. But can we ever truly get 100%? Right? Can we ever get 100%? So look at what this graph does as you go to 100. Let me graph x equals 100. And let me make that a dotted line. So there's x equals 100. So if we try and get to 100%, look what happens to this number. If we try and do, let's say, 50% of the lake, $10 million to clean half of it. But as we try and go more, look, 20 million, 30 million, now it's taking off, right? It's getting really hard to get everything. And so you get this function that, yeah, in the beginning, it's if you want to do a small percentage, yeah, we can handle that. It's not going to be that expensive. But if you try and get all of them, it's going to get impossible to do. So does that make sense to you all? This is just a function that kind of models what's happening with this situation. Also, I should point out that the other parts of the graph don't matter. Like this part of the graph is irrelevant to us because it doesn't make sense within this problem. So what I would really want to do is only look between 0%, and 100%. That's the only part of the graph that actually matters to us, from 0 to 100. So again, this was just to give you some perspective of where you can see a real rational function in a real world situation. It becomes like economically, like not feasible to ever try and clean these mussels out. It just gets too expensive. That's why we won't ever do it, right? So, all right, that's it. There's the function. If I were to give you this function on a test, 10x over 100 minus x, and ask you to graph it, I would expect that you could do that, right? Because this is just a rational function. So you find the x-intercept, find the verticals, find the horizontals, test points, draw it, you're done. Questions? Okay. So we're ready to talk about our second to last function of the semester that we're going to need to be able to graph. This will be on your next test, but I think you're going to be pleasantly surprised to see that these are going to be easy for you to do. All right, compared to what rational functions are, you're going to be like, oh, okay, these I can do. What you're going to need is your calculator. So I need to go grab mine because mine is in my backpack. I'll be right back. Okay, sorry about that. It was out in my car. All right, so we're going to talk about these new functions. I'm not even going to tell you what they are yet. I'm going to try and motivate where they come from, or where, again, we'd see them in the real world. So I want to just kind of give you some comparison first. So I'm going to compare three different things here. Let's first talk about linear functions, and then we'll talk about quadratic, and then we're going to talk about this mystery function that we're going to talk about today. So I'm going to give you an example of a linear function. F of x equals 2x. Then I'm going to give you an example of a quadratic function, f of x equals x squared. These are specific examples, all right? There's a lot of different lines we could have. There's a lot of different quadratics. So I'm just giving you two specific examples. Now, if you go back and you think about when you're first learning about functions, one way you can figure out what's happening is to make this thing called a t-table. Let's see if this makes sense to you. A t-table is something where you can kind of represent what's happening. You plug in an x, and then the output will be whatever the function is. So x here, x squared here. And we can start plugging in some values. So I'm going to start plugging in some values, and I just want to talk about what happens. So I'm going to start with 0. If I plug 0 into this function, what does it spit out?
0.
0. Okay. What if I plug in 1? What does it spit out?
2.
2. If I plug in 2, 2 times 2, right? 4. If I plug in 3, 3 times 2 would be 6. One more, 4. Plug in 4 times 2 is 8, right? So this gives us an idea of what this function is doing, right? It's just doubling whatever we put in, it's doubling it. If I plug in -1, right? What would -1 times 2 be? Just -2, right? Plug in -2, -2 times 2 is -4. Plug in -3, -3 times 2 is -6. And I could keep going, right? That table gives you a basic idea of what's happening. Let's compare that to this one. If I plug in 0, 0 squared is 0. What about 1? 1 squared is 1 times 1, that's 1. How about 2? 2 squared is 4, right? 3 squared, 3 times 3 is 9. 4 squared, 4 times 4 is 16. I could keep going, right? These are not the same, right? Like on this linear function, when I plug in 0, I get 0. Yeah, that matches this one, right? When I plug in 1, I get 2. Okay, that doesn't match. When I plug in 2, I get 4. Here I get 2 and 4. Those match, right? But the rest of the way it doesn't. 3, 6, 3, 9, 4, 8, 4, 16, right? They don't match. What about negative numbers? If I plug in -1, -1 times -1 is +1. -2 times -2 is +4. -3 times -3 is +9, right? These don't match either. So these are different functions, right? They don't look the same when we graph them. And we could confirm that by just graphing them, right? I'm gonna do a new one here. If I do y equals 2x versus y equals x squared, obviously the graphs are different, right? So let's talk about this new function. And the way we're going to do it is we're going to do it kind of backwards. I'm going to create the table first without telling you what the function is. And what I want us to do is see if we can come up with what the function is, right? So like on this one, if you were to look at this table, you know, if you think about it enough, you might be able to figure out, oh, look, what I'm doing here is just squaring each of these. And over here, you might be able to look and say, oh, all I'm doing is doubling each of these, multiplying by 2. So maybe if we can do this table, maybe you can help me come up with the actual function that's doing, you know, like what it needs to do to create the table. So here's the way we're going to do it. It's going to be a fun little exercise. Well, it's not going to be fun. I'm just going to say it's fun. Okay. All right. So here's what we're going to do. Can y'all see my video okay? Should I stop sharing my screen? It's okay. Can y'all see a white rectangle? That's a sheet of paper, right? We see a white rectangle. All right. So right now, I have not folded this piece of paper, right? I have not folded it. It has not been folded. And you see one rectangle. So my table here is actually going to be the X, and then the question we don't know. The X is going to be the folds that I have, and this is going to be the rectangles that you see. So right now I have 0 folds, and you see one rectangle. Agreed? 0 folds, 1 rectangle. Already, does that match either of these? No, it doesn't, right? Okay. So now I'm going to fold it one time, right in half. I'm going to draw a line on the crease so you can see the fold, because it might be hard on camera to see it. Wherever I have that crease, I'm going to draw a line and open it up. I don't know how that's coming out on camera, but I folded it in half and I open it up. How many rectangles do you see now?
2.
2. Okay, so I folded it one time. I better keep that handy. I folded it one time and I have 2 rectangles. Okay, so now what I'm going to do is I'm going to take it again. I'm going to fold it once, and now I'm going to fold it a second time. I'm going to open it up and I'm going to draw my little lines so you can see them. Anybody have a guess as to how many we're going to see?
4.
4 rectangles. See them? Okay, yes, yes. So when I folded it twice, I got 4. Okay, let me do it again. 1 fold, 2 folds. Here's my 3rd fold. Any guesses? I'm gonna open this. What's that?
6.
6, okay, that's a common guess.
8.
8,
9.
how many do you see?
8.
8.
8, right? 4 across the top, 2 along the side. So now I have 8. So when I fold it 3 times, I got 8. Let me go again. 1 fold, 2 fold, 3 folds. Here comes my 4th fold. What do you think? You see a pattern in this yet?
16.
16?
16.
16? Let's see. I told you this would be fun.
Is it doubling by 4 each time? So like quads? Well, no, it wouldn't be quads, would it?
It's just
Yeah.
doubling.
It's just doubling, like on the right side, it's just doubling.
Okay, very good. You said that the correct way. So you see 4 across the top, 4 across the bottom or side. So that's 16. 4 times 4 is 16. So when we folded it 4 times, we got 16. So someone said it's doubling each time, but on the right side. So it's like you're taking that, multiplying by 2, taking that, multiplying by 2, taking that, multiplying by 2, take that, multiply by 2, right? Does everyone see that pattern? Does that pattern happen on these?
No.
No, like, look at this one. From here to here, you're not, from here to here, you're not multiplying by 2. What are you actually doing?
Adding 2.
Adding
You're
2.
adding 2. You're adding 2 each time, adding 2 each time, right? That pattern's there, right? But it's not multiplication by 2. This one, it's not even that. It's like here you added 1, and then from here to here you added 3, and then from here to here you added 5, and then here you added, looks like you added what, 8?
7.
No, 7, sorry. But this is different. You're multiplying by 2 each time. So what should we predict the next one would be? If we folded it 5 times, we should expect to see what?
32.
32 of them. Now I'll do it one last time. 1, 2, 3, 4, 5. It's getting hard to fold this. All right, there we go. Open this thing up. Okay, so we have lots of little boxes here. I believe there's 8 across the top and 4 down the side. 8 times 4 would be 32. So we have 32, which is what we should expect. What about 6 folds? We should expect 64, right? I told you it was the last time. Let me see if I can do 6. 1, 2, 3, 4, 5, 6 is gonna be hard. I got 6. Okay, 6. I'm not gonna draw lines, but if I open that up, that's gonna be 64. 7 folds, I don't think I can do. It's not physically possible for me to fold this. It's too hard, okay? So my question to you is this now. What would happen if I could fold it 15 times? What would you get? Well, one way to do it would be to just complete the table, right? Go figure out what 7 would be. So you would double this, right? What is this times 2?
128.
Yeah, so you could do 7. So remember, my question is 15, right? What would happen at 15? You could do 7, that'd be 128. And then what, at 8, you could get, what's that?
256.
256. 9 would be 512. But see, I have to go all the way to 15, right? That kind of sucks. That I have to complete the table. Do you understand what I'm saying? Whereas over here, if I were to ask you on these problems, if I were to ask you what happens if you plug in 15, all you have to do is take that 15 and plug it in there, right? You have a function that tells you what to do, right? If I want to know 15 here, I just take that 15 and I plug it in there and I'd tell you the answer. Here, if I need 15, I need a function to plug it into, but I don't know what the function is. All I know is that it keeps multiplying by 2 each time. Y'all see what I'm saying? Like, we want a function that will do this for us. So can we figure out the function? So I'm going to help you see it, okay? I'm going to help you see it. What I want you to think about is over here on all these numbers on the right-hand side, I want you to realize that 2, this first number 2, is actually 2 to the first power. And 4 is 2 squared, right? 2 times 2 is 4. And 8, isn't that 2 times 2 times 2? And see, each time we come down the table, we're multiplying by 2 more each time, right? So isn't this 2 to the 4th? And 2 to the 5th? And 2 to the 6th? Y'all understand? So isn't the power that we see here, isn't the power the actual number that we're plugging in? So that this last one, this right here, this 15, if I wanted to know that, wouldn't I just do 2 to the 15th power? 2 times 2 times 2, 15 times, right? Which means that the function that we're trying to figure out up here, it should be 2 raised to the x power. Please see the difference between these 3. This one is 2 times x, that's linear. This one is x raised to the 2nd power, that's quadratic. And this one is different. This is 2 raised to the x. Notice where the variable appears. The variable is up in the exponent, right? It's up on the top. Here, the variable was down on the bottom. And here, the variable is down the bottom. We've never in our lives, well, unless you've studied this before, we've never seen a function where the variable is up top. This is new, okay? This is new, and it's a special category of functions. By the way, how do we do 2 to the 15th on our calculator?
Don't you hit the caret button?
Yeah, so hold on, I'm trying to find my, oh, here it is. So this is the calculator that we're all supposed to be using, this one here. So if you have this one, there is a button there. It is, yeah, you said caret, that's right. There is a button on the left side of the screen, or on the keyboard, there's a button that looks like this. And it's called the caret key. I believe that's the way you spell caret. All right, that's your caret key. And what that does is allows you to raise something to a power. So if we want to know 2 to the 15th, what we're going to do is type this in. We're going to type 2 caret 15. So just type that in, 2 caret 15. When you hit your caret key on the calculator, you'll see if you type in 2, type 2, and when you hit the caret key, don't hit anything, you'll see this on your screen. You'll see 2 with a little box, and it'll be flashing. that little box will be flashing. And that's telling you put a number in there. So I put 15 in there. So that it'll look like this on your calculator, and then hit enter. And you get your number, which is 32,768. Wow. So if I could fold this 15 times, if I could, I physically can't do it, but if I could and opened it up, I would see 32,768 rectangles in here. That's a lot of rectangles, right?
If you could fold a piece of paper 42 times, it would reach the moon.
Say again?
If you were to fold a piece of paper 42 times, it would be thick enough to reach from Earth to the moon.
That sounds about right, because what would 2 to the 42 power? Try that on your calculator. 2 raised to the 42. So if you try that, 2 raised to the 42, your calculator is going to say something like 4.398, blah, blah, blah. And then at the very end, it says times 10 to the 12th, which really means take 4.398 and move the decimal point 12 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm just going to put zeros in here. So that's like 4, 3, 9, 8, 2, 3, 4, 5, 6, 7, 8, 9. How much is that? This is like ones, tens, hundreds, thousands, 10,000s, 100,000, million, 10 million, 100 million, billion, 10 billion, 100 billion, trillion. So this would be like 4 trillion pages thick. What do we mean? Okay, so you have to understand when you fold it no times, how thick is it? 1 page, right? If you fold it once, it's 2 pages thick. If you fold it twice, it's 4 pages thick. 3 times, it's 8 pages thick. So this, you could also look at this number as being the thickness. So if you could fold it 42 times, Nix is saying it would be 4 trillion pages thick. And if each page is, think of about a book that has 4 trillion pages in it. Nix is saying that that would reach the moon.
And if you were to fold it 100 times, it would reach past, let me see reach past the just observable universe.
Oh, 100 times?
Yeah,
So,
I know a lot of random facts.
That's good. That's good. This is very, very fast growth. What's happening here? I'm going to graph this function here. All right. But before I graph it, looking at these two functions, the linear and the quadratic, which one of these grows faster? So as you move to the right, which one of these goes up quicker?
The quadratic.
The quadratic. Do you all agree? Like if you were to pick a value and plug it in, you would be here on the line, right? But way above that up here is where that point would be. Do it this way. Stop. So if you were to pick a point on this, right, here's where it would be here on the line, but up on, that's, sorry, I don't know, just keep on getting these like random sneezes here. So you would have, on the line, it would be down there, but on the parabola, it would be way up there, right? So the parabola is growing much faster. And you can tell by the table, right? If you look at these numbers, it's like 2, 4, 6, 8, 10, 12. This one is like really fast. 1, 4, 9, 16. It's growing. Next one's 25, 36, 49, right? So these are growing really quick. This was just kind of like slowly trickling up. This one, though, y equals 2 raised to the x. Look at it compared to the parabola. It's growing even faster than the parabola. In fact, so fast, it's really not even comparable. Not even comparable. If you were to try and, well, plug 15 into this. Plug 15 into this right here. Square 15, take 15 and square it. What do you get? Oops, I were to do this.
225.
What's that?
225.
Yeah, 225. That's what you get when you square 15. Look at that. At 15, you're at 225. And over here at 15, you're at 32,768. So this right here, this function 2 to the x has a name, okay? This is an example of what is called an exponential function. An exponential function. I'm sure that in your life you have heard this before. If you watch the news, turn on, you know, anything, any TV, you're gonna hear it randomly throughout different places. Like you'll hear like, oh, the crime rate in San Antonio is growing exponentially, right? They'll always throw this word out there, exponential growth. Now they don't use it properly most of the time. It just means that it's growing, that they mean it's growing fast, okay? It's growing quickly. The COVID-19, right? The way that the COVID-19 virus spreads to people is exponential growth. So let's talk about that, because I think if we tie it into COVID-19, you'll even see even more how exponential functions are important. Let's say in the beginning of the COVID-19, you had one person who was infected, all right? So there's a person, right? They go about their day, and this is before any restrictions or anything like that, before we even knew what was going on. That person goes out and maybe they are in contact and they actually spread it to, let's say, 4 people, right? Now, each of those people go out and they spread it to 4 people, right? Let's say. And then those people go out and spread it to 4 people. Now this is gonna, I don't want to draw these dots, okay? And let's say, you know, this is, when I say this person spreads it to 4 people, let's say it took 1 day for that to happen. So they went out, they went about their business, they spread it to 4 people. A day later, each of those people spread it to 4 people. A day after that, each of those people. So if I make a table, and this is days, and this is number of people, then at day 0, okay, when we started this, 1 person had it. How many people had it after 1 day? These 4, right? How about after 2 days? Well, each of these 4 spread it to 4, right? So we have to multiply this number by 4, which is 16, right? There's 16 people here on this line. The next day, 4 more people have it, which is 64. So how much are we multiplying by each time?
4.
Not 2 this time, right? It's 4. So what should our exponential function be then? What raised to the x? What number here?
4.
Yeah, 4 to the x. That should be the exponential function that describes the growth of this virus, the transmission of it. So what would happen after 2 weeks of this? Well, how many days? 14 days? So what would 4 to the 14th be? Go to your calculator.
I got 268435456.
Yeah, 268435456. $268 million people in 2 weeks. That's a lot of people, right? That's San Antonio's. What's San Antonio's population? I don't even know. I think, is it like 2 or 3
2
million?
million? Yeah, I think
Yeah.
it's like 2.3 million.
Yeah, 2.3, somewhere in there. So look at this. This is 268 million. So if you had a virus out there that you didn't know was there, right? And one person spread it to 4 people every day, and that happened for 2 weeks, that's enough transmission that you could basically infect 10 times the population of San Antonio in 2 weeks. So exponential growth. Okay, the way diseases are spread or transmitted is exponential growth. So in general, how are we doing on time? In general, an exponential function of base A, this is terminology, in general, an exponential function of what we call base A is a function f of x where you take some number a and raise it to the x power. Now the a that's down there is called the base of the exponential function. And that a can be any number you want, but there are some restrictions. A must be positive, and a cannot be 1. Now, the reason why it must be positive is because it gets really weird when you start taking negative numbers to different powers. And then it can't be 1 because 1 raised to any power is still 1. Like 1 squared is 1, 1 cubed is 1. So this is what an exponential function looks like. I have shown you 2 examples of that, right? I've shown you the paper folding paper. That was 2 to the x, right? 2 to the x. And then the COVID thing transmission, that was 4 to the x. This is saying you can have any number to the x as long as the number is positive and it's not 1. We good? Is this making sense so far? Now, let's do another example. I'll go back to that page. Let's do another example. This is kind of like the main definition of an exponential function here. Let me do another example where I'm going to take table here. This is going to be number of cuts, and this is going to be the length. All right, so I want you to go and think about this. Let's say I have this sheet of paper. Let me get a new one. Okay. Let me do something real quick. That was terrible. Okay. Let's say I took this sheet of paper and I measured it and it was 1 foot long. I know it's not, but let's act like this is 1 foot, okay? 1 foot. Right now, I have not cut it at all. So it's 1 foot, I have 0 cuts. 0 cuts, it's 1 foot. 1 length in feet. Now, I'm gonna cut it right down the middle, okay? Cut it in half. Throw away 1/2, and I'm looking at the other half. How long is this now?
6
Half a foot.
inches.
6 inches or 1/2 foot, right? 1/2 foot or 6 inches. I'm going to write it in feet. So I'm going to say after 1 cut, this is 1/2 foot. Now I'm going to cut it a second time. So I'm going to cut it in half.
You've got
So
a
I've taken
quarter of a
the
foot.
half and I've cut it in half. What's that, Nix?
You've got a quarter of a foot.
a quarter foot, 1/4 of a foot. Because I took a foot, I cut it in half, which left me with a half, and I took half of a half. Half of a half, half of a half means half times a half, which gives you 1/4. So if I cut it twice, I'm gonna get 1/4. Ready? Go again. Cut that in half. How long is that?
1/8 of an inch.
1/8 of a foot, right? It's 1/8 of a foot. 1/8, because I did half of a fourth. So I took that fourth and I multiplied it times a half. See, I took this half, I multiplied it times a half. Now I'm gonna do it again. One-16th of a foot. Yeah,
It's like sort of the same thing that's happening, but only with the denominator of the fraction.
exactly. It's like only the denominator, right? Keep going. That was like a multiply times a half. What would happen if I do it again? 5th cut right down the middle.
1/32.
1/32 of a foot.
But it also wouldn't be considered exponential growth, right?
It is exponential growth. Exactly. Now, the question is, what is the function that's doing this? So what is the A? What is the base we have for this? So if you go back and look at, yeah, hold on. If you go back and look, remember when we said we were going from here to here, we're just multiplying by 4 each time? And that was 4 to the X. When we did the original paper where we were folding, we said, oh, it doubles each time, right? Times 2, and it was 2 to the X. So here we are multiplying by a half each time. So it seems like it should be what? The A should be half, right?
1/2.
A half. So 1/2 to the X. Let's try it. Let's see. Just try it on your calculator. Okay, try it on your calculator. Do 1/2 raised to the 1. So you got to make sure you can type that in properly. How are you going to type that in? 1/2 to the 1.
Isn't it open parenthesis 1 divided by 2, close parenthesis, and then the caret?
That's right. Parenthesis 1 divided by 2, close parenthesis, caret 1. Hit enter and it should give you 1/2. How about 1/2 squared? Parenthesis 1 divided by 2, caret 2. Do that on your calculator, see what happens. One-fourth. Now, this is nice, okay? This is nice because it's giving us the same answers as over here. Do y'all agree? But sometimes we would rather have the decimal. So let me show you what you can do if you want your calculator to give you a decimal really quickly. Instead of typing this in, type this in. Type 1.0 divided by 2 raised to the 2. If you make any one of those numbers a decimal, your calculator will do the decimal for the whole thing. There's other ways to do it, but I find that to be pretty straightforward. So if I do that, my calculator says 0.25, which is the same answer as 1 divided by 4. So this will give you a decimal. But the key is that you have to type in 1.0. Okay, so I have a question for you. What if I cut this thing 30 times? Am I going to still have some left or not? I keep cutting in half and half and half, and I do it 30 times. If I could do it on your calculator, give me the decimal answer. If I could cut it 30 times.
So it's like 9.31, and then it shows like E -10.
Yes, so let me explain what's happening there. We're doing 1/2 to the 30 and your calculator is saying 9.313. And there's a bunch of numbers and at the end it says times 10 to the -10. What this means is move your decimal point to the left 10 spaces. So that means take this answer, move your decimal point 10 places to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you really have 0.000000000931. That's a very small number, isn't it? Really, really small.
It's an infinitesimal number.
Yeah, it's an infinitesimally small, kind of like when I was talking about winning the lottery and getting struck by lightning, right? It's this really, really small thing. So let's look at the graph of this. I'm curious to know what the graph of this looks like. I'm going to take the line out of here. I'm going to take the parabola. Here was the good old exponential function 2 to the x. This is what 2 to the x looks like. Let me graph 1/2 to the x. Look what it's doing. As I go out to the right, do y'all see what it's doing? When we plug in 1, we got a 1/2, right? When we plugged in 2, we got a 1/4. Plugged in 3, we got 1/8. 4, we got 1/16. And then when we tried just plugging in 30, right? We got this infinitesimally small number. In fact, the computer is saying it's 0, but it's not. It's like 0.000000009 something. But we keep on getting closer and closer to the x-axis without actually ever getting there. Does that look familiar? Did we see something like this before? Didn't rational functions have this? Sometimes they did, sometimes they didn't. It looks like these exponential functions, if you look at both of these graphs, don't they both look like they have this like horizontal asymptote? The green one has one out the left side, and the purple one has one out the right side. So we're out of time. We have 2 more minutes. We're going to get more back into this next class, talk a little bit about more about these and just how to graph them. Like what do they all kind of look like? They all kind of look, remember, all parabolas kind of look the same. Polynomials all kind of have a characteristic to them. All exponential functions have like this flavor to them that we need to understand. I want to say one more thing before we close it up. And this is off topic, on topic. I wanted you to look at something here and tell me if you recognize somewhere in the real world where you've ever seen these numbers show up.
Video games.
What do you mean?
It reminds me of 8-bit, 16-bit, 32-bit, 64-bit, and then now we're running games that are like terabytes of data. Well, technically gigabytes, because I can't think of a game that's a terabyte in storage.
Yeah.
It reminds me of the game 2048.
Oh yeah, that's a good game.
That one too, yeah.
Yeah. So if you think back to like when you buy your phone, right? You can buy these different, like you can buy your phone, they can say how much storage do you want on your phone, right? Do you want the iPhone with the 128 gig, or do you want the iPhone with the 256 gig? Does this sound familiar to you? Okay, these numbers, why don't they say, hey, would you like the iPhone that has 200 gig? Why is it always weird numbers like 128, 256? Right? I mean, it's usually those numbers.
I don't know. I don't know about phone storage, but what about like on a computer where they partition the hard drive so it does take up some of the space?
Yeah, well, then you can control it a little more, right? Where you partition, how big you want it, or are you saying that those partitions also have to be in these numbers?
Yeah, that's what I was thinking of, because it does take up storage too.
Yeah. So look, we're out of time. If you need to go, you can go. The whole reason these numbers show up in computers and on our phones and stuff is because a computer, at the end of the day, the computer only understands, and this is what's amazing about technology, how far we've come with it, is at the end of the day, at the end of the day, all your computer knows is this. I don't know if y'all can see this on my screen, but it either knows off or on. That's it, off or on. So a computer only understands that there either is an electrical signal there or there is not. It's a yes or a no. Or if you like, you can look at, the computer really looks at things as either being a 0 or a 1. And that means there's only 2 states that anything can ever be in on a computer. 2 states. That's called binary. Binary meaning 2. And anytime you have something that's based on a system that has just 2 things possible, then everything within that system is going to be related to 2 to the x. And so 2 to the x, when you think about that exponential function, takes on these weird values that are on our table, right? 16, 32. So when they do the storage, they do it in powers of 2. So even if you buy a 1 terabyte drive, even if you get a 1 terabyte drive, the actual storage on there is going to be a power of 2. It'll say a terabyte, but it's actually a power of 2. So anyway, okay, y'all have a great day. I will see you on Thursday. Yeah, only homework well, there is no homework actually. Now I think about it, because we didn't really get into anything brand new. So y'all just have a good day. Review the stuff we've done. How about you do that?
Yeah, that's what I was gonna ask, if we could have this one uploaded. I could go through the homework on that.
Have what uploaded?
This episode or this
Yeah,
class. Okay.
Yeah, I'll upload it.
Alrighty, thank you.
Okay, everyone.
That's cool.
Have a good day.
I've never thought of computers like that. That's cool.
Really? Yeah, it's all based on that base 2 system.
That's cool.
Yeah, it is. It is. So, yeah, I mean, it's fascinating. We won't get into it more because I've got to go, but we can pick that conversation up at another time.
Cool. Bye.
Bye. Have a good one.
You too.